So today we're going to do a brief demo of how to use SankhyaSutra Taral to perform simulations for the flow past and Ahmed Body. The agenda is going to be the following. I'll just briefly walk you through what SankhyaSutra Taral is and where and how exactly it can be used to fulfill your simulation needs. I'll then give you a brief background of automotive flows in general and how CFD comes into the picture uh, in the automotive industry. Then I'll go through the simulation workflow, which is basically the steps that are needed to set up your case on SankhyaSutra Taral and run your simulations according to your needs. I will then do a hands-on demonstration of the simulation of the Ahmed body problem. I will show you how to set up the case parameters, how to import your geometry, and how to interpret the results and post-process them according to uh, the format that you need them in. So SankhyaSutra Taral is essentially a Lattice-Boltzmann method solver. It is different from conventional CFD solvers in the sense that conventional CFD solvers aim to discretize the governing equations of fluid flow, which are the Navier-Stokes equations, and then introduce some approximations to arrive at the desired solution according to the regime that you're simulating. So the Lattice-Boltzmann is different in the sense that we solve a modified variant of the Boltzmann equation, where where we discretize our space using a structured grid. We don't have to worry too much about meshing. It's a much simpler approach compared to conventional solvers. The space itself can be discretized using a finite number of velocities, which is basically your particles are restricted to move in certain directions. Then we solve for the probabilities of those particles to exist at certain points in space at certain instants in time. We then integrate those variables, and the macroscopic moments of those variables essentially give you your macroscopic parameters of interest, which are density, temperature, pressure, and velocity. So we can so there's also different variants of models within the solver depending on which regime your problem falls into. So for a problem which constitutes a high Mach number flow or a high Reynolds number flow, you can always use a higher order model, which will be computationally more intensive, but your solution will be accurate for that particular regime. So the distinguishing characteristic of our solver is that we guarantee numerical stability without the use of approximations or turbulence models. And we make use of the crystallographic Lattice-Boltzmann method, which factors in an efficient space packing lattice structure, which is also known as a BCC structure. I'll go through that a little more in the consequent slides. If you want to refer to any of these particular concepts, the references are available at the bottom left of the screen in this particular slide. Yes, so the characteristics that give us a unique placement in this category of products is that the first thing is that we guarantee numerical stability, and that is guaranteed by from the second law of thermodynamics, which is from first principles. There's no approximations or modeling involved. Then conventional Lattice-Boltzmann solvers use the simple cubic mesh. We make use of the crystallographic Lattice-Boltzmann method, which makes use of the body-centered cubic mesh. This basically gives you 4 to 6 times less discretization errors for complex and curved geometries with only twice the number of points as compared to a simple cubic mesh. We also offer higher order LB models, which are lattice structures with a higher number of velocities in the discretized velocity space. This essentially gives you the option to run simulations at high Reynolds numbers and high Mach numbers, extending up until the transonic regime. We also make use of novel data structures and efficient task decomposition methods in order to parallelize the solver to the best of its abilities and make complete use of the resources that that are allocated to the simulation at hand. The key features and benefits of the solver, as I already spoke in the previous slide, are that yeah, we solve for the underlying physics without any approximations, which is basically we don't we don't discretize the Navier-Stokes equation and introduce modeling in order to arrive at the solution, but we essentially uh, solve the Boltzmann equation, which stems from the kinetic theory of gases, and we get the exact solution to arrive at the microscopic moments that we want to, that are of interest to the user. We also offer automatic generation of structured grids with custom user-defined refinement at specific locations or for specific regions in your geometry. Compared to a conventional Navier-Stokes or a RANS solver, where a lot of effort goes into deciding your meshing strategy and deciding which regions to refine, this this is a much easier way in the sense that it's just a few clicks away, and it's quite nifty in the sense that it gives you a quick mesh without much ado. We are also capable of efficiently handling complex geometries and also arbitrarily moving geometries such as turbine blades, propellers, etc. We since we also offer higher order Lattice-Boltzmann models, which are again models where we have a higher number of velocities in the discretized velocity space. We can also perform simulations up until the transonic flow region. And our solver itself and the formats in which we output our data gives the user an easy way to extend their simulations to perform aeroacoustic analysis and include the product in their workflow to perform other multi-physics simulations. Now, I just want to give a brief background of the situation of automotive flows in the CFD industry in general, and why CFD was started to be used to perform automotive simulations in the first place. So around the 1980s, uh, prior to the oil crisis, decisions on external geometric features for any vehicle or any automotive geometry were majorly dominated by safety and aesthetic considerations rather than aerodynamic efficiency. But the reduction of fuel consumption became a major concern for automotive manufacturers due to the oil crisis in the year 1979, where oil prices rose by a lot, and that essentially led to automotive manufacturers needing to improve the fuel efficiency of their vehicles. Also, and in recent years, growing ecological concerns such as global warming and climate change have also made this a critical issue to reduce the amount of fuel that is consumed and to eventually phase out fossil fuels in general. So the major contributor to fuel burn is, of course, aerodynamic drag, which depends on the shape of your vehicle and how much force it experiences and how much fuel it has to burn to overcome that force and move at the desired speed. So in the 1970s, there's these two authors, Ahmed and Morel. They and their teams conducted some novel experiments with certain geometries, which essentially paved a new direction for automotive design and automotive simulations in general. Now, so the Ahmed body is essentially the geometry that Ahmed et al. Came up with in 1984. It's an extremely simple and simplistic geometry, which is capable of generating complex and relevant flow features that mimic those of a modern automobile. Which basically it's an easy geometry to recreate and use in wind tunnel experiments, and that makes it quite easy to also mesh and run simulations for. So this particular geometry has a lot of separated flow regions, which is one of the major contribution factor to the drag of any vehicle. And there's several complex vertical structures that arise in the wake of the vehicle, which is in the rear end of the vehicle, which are highly dynamic in nature, and They are quite complex in the sense that there's a lot of 3D interactions, which makes it highly challenging for the solver to accurately capture and predict. So another point I would like to reiterate is that uh, the wake phenomena in any vehicle is probably the most important region that the simulation has to accurately predict in order to capture the macro features of the flow around the vehicle. So this, the figure on the top right is just a schematic of the Ahmed body, and on the bottom right just gives you a basic idea of what kind of flow features exist over a conventional automotive geometry. I won't spend too much time on this. This is just a brief diagram of what the Ahmed body is. It basically consists of a round front part to prevent separation, a long midsection, and an adjustable slant plane. And the angle that this slant makes with the horizontal plane is essentially known as the rear slant angle. And today we're going to be showing you a demonstration of performing simulations for an alpha of 25 degrees, which is one of the critical configurations as it exhibits both separation and reattachment over the rear slant of the vehicle. And this is quite challenging for any solver to capture, and especially for RANS solvers to capture. So, just a brief motivation of why CFD, why we want to why we want to introduce CFD into the workflow of designing an automotive geometry. If you look at the situation even today, wind tunnel experiments are highly prevalent, and they're also quite expensive. So there is an obvious need for alternative solutions, which are both low cost and accurate. In the industry, RANS is probably the most commonly used solution for this particular problem, as it gives you quick solutions and the macro features are captured quite well for most geometries. But it certainly has its limitations in the sense that obviously it can't capture unsteady phenomena as it's a steady state methodology. And as I spoke about in the previous slides, capturing unsteady phenomena is quite important to capture the flow features of any automotive geometry, as it's vital in predicting the base pressure, which is the pressure in the wake region, and therefore is also vital in predicting the drag force. So we can always perform DNS, but DNS is infeasible as it's quite expensive. The number of points that can be used that have to be employed for a particular simulation for a DNS simulation are of the order of the cube of the Reynolds number, which for this particular case would go around 100 to 200 billion points. LES again is one of the most commonly employed solutions for this, but its accuracy again is highly dependent on the choice of turbulence model. So it again becomes a exercise for the user to determine which model to use and to validate their results and check whether they're actually correct and matching with the reference. So that's where we come in. The method that we make use of is known as the entropic Lattice-Boltzmann method. It's essentially inherently stable for high Reynolds number flows without the need for any explicit turbulence modeling, due to the reasons that I mentioned in previous slides. Okay, so that was just a brief background of automotive flows and the motivation for using CFD in the workflow of automotive design. So I'll just give you a brief overview of the kind of parameters that need to be set for running a simulation using SankhyaSutra Taral. The first step, of course, is to import a clean geometry. That is essentially the pre-processing step. Then you set your parameters, which are user-defined parameters. There's 4 categories of parameters that have to be set. The first one is parameters for designing the kind of grid that you want to run your simulation in. And then come the properties of the fluid that you want to essentially simulate, which are the material properties. What we call measurements are essentially tools to help you monitor your simulation and to help you store data that is of interest to you at instances of time that are of specific interest to you. Then at the end, we also have to set the global simulation parameters, which are kind of general in the sense that it's essentially the amount of compute that you want to use and the amount of time that you want to run your simulation for, etc. So I'll do a deeper dive into these parameters as and when we do the hands-on session. And ultimately, we also offer a post-processing tool, and we have a graphical user interface for the same. This essentially helps you process your data and modify it such that you're able to use it in the format that you desire it to be. So for the pre-processing steps, there's essentially there's essentially multiple ways that you can do this. For complex geometries, the usual modus operandi is you generate your CAD from any third-party robust CAD tools such as ANSA, SolidWorks, Creo, etc. Then you triangulate, you basically tessellate your surface model in whichever format you've designed it in into a triangulated format and save it as an STL. So Taral takes STL format files in the ASCII format as an input for geometries. Whereas for simpler geometries such as cubes, cuboids, cylinders, spheres, etc., you can always create basic shapes on ParaView, which is an open source tool available to everybody, and export it as an ASCII STL. Or if you're feeling particularly adventurous, you can always write your STL manually and save it as an ASCII STL format such that it can be imported into Taral. When Taral takes the geometry as an input, it performs basic checks on the file. It checks for water tightness, quality, etc., and throws you any relevant errors if applicable. For the simulation parameters, as I said, there are 4 categories. In the grid parameters, you can set your resolution. So you can always set patch-wise resolution. So patches are essentially certain regions in the STL that are demarcated by the user based on their specific interests, such as applying different boundary conditions on different surfaces, etc. So Taral offers features such that you can set custom resolutions for specific areas in your specific surfaces of your STL. Brushes are essentially a feature where you can select specific regions in your STL, specific cuboidal regions in your STL that you want resolved with a certain level of accuracy. Number of refinement levels essentially determine the number of resolution jumps that occur from the finest resolution in your simulation to the coarsest resolution in your simulation. So all of these things will become much clearer as and when I show you the demonstration itself. Then you set your material properties, which are the properties of the fluid that you plan on simulating for. So the inputs that SankhyaSutra Taral requires mandatorily are density, kinematic viscosity, and molar mass, all in SI units. Then you essentially set the parameters for the measurements that you want employed in your simulation. We offer 4 different kinds of measurement solutions. The first one is probes, where you can select certain points to plot the time history of quantities of interest at. Volume measurements are essentially where your entire simulation domain gets printed at selected time instances. Surfaces are where you can print out the information in a CSV file format of the points that are closest to whichever surface that you select to print this information for. And finally, you can always select to print integrated forces and moments, and you're able to monitor the time histories of these forces and moments in a live manner on the GUI tool itself. So yeah, you can always set the sampling interval for each of these measurements, the start and end time, which is basically the window of time where you want these measurements to be printed, and you can select specific regions and patches for which you want these measurements to be printed, but this is applicable only for surface measurements. And then finally, you set the simulation parameters, which are essentially your reference flow quantities, which are basically the quantities that you want to compare against. Then you set your boundary conditions for all patches that you import. The initial conditions for your domain, you set your velocity, temperature at the instance whenever the simulation begins. I'm sorry. And then you set the time for which you want your simulation to run in the simulation space in seconds. And we also have this feature where you can print out, you can save instances of your simulation at user specified instances of time, and you can always restart from those instances at a later point, even if your simulation gets killed, or if your wall time exceeds the specified wall time for the simulation. Okay. Yeah. So just a brief background of automotive flows and the SankhyaSutra Taral solver itself. I'll just move on to the demonstration of the Ahmed Body problem, of simulating the Ahmed Body problem using the solver. So
In the meantime, when Kaushik is opening up the demo window, if the attendees have any questions, please do type them in. Kaushik would be glad to take them up.
yeah, sure. Okay. Does anybody have any questions or?
We can move on, Kaushik.
Okay. Cool. Thanks. Okay. So this is the loading window of the SankhyaSutra Taral product itself. You will be assigned a username and a password. You will have to enter those credentials into their specific fields and click on the login button. It will then take you to the dashboard where you can see a list of projects that you might have created. You also have a window where you can view the projects that have been shared with you by other users, if any projects have been shared with you. This gives you an estimate of how much data storage your account is using at the current point of time, which for me is around 228 GB. So to create a new project, yeah, you can always load from existing templates. Uh, I already have the Amit template here, but I will try to set it up from scratch so that you get a better idea of how to set up an automotive case by yourself. So I'm going to click on the new project button. You have to type in your project title. I'm going to say Ahmed Body Simulation. You have to specify a brief description. I'm just going to say drag and analysis. And you have to select the unit system that you want to employ for your current simulation. Presently, we support the SI unit system. And yeah, we plan on adding other units in the near future. So then we click on create project to create the new project. And as you can see, it has been created here. To actually go into the project and start setting up your simulation, you will have to click on open in workspace. So I'm going to click on that. So this is the main screen. This gives you a tree view of all the parameters of your simulation that have to be set by the user. So if you click on expand all, you can see all of the individual subcategories of these individual items in the tree. We also have a post-processing tab where you can view your simulation results and perform post-processing operations on the same. So I will go to that as and when I will show you the rest of the simulation setup. So the first step of your simulation is to import a geometry. I'm just going to go to geometry and click on the plus here. So you can always create some basic shapes from within the GUI tool itself, such as sphere, cylinder, box, etc. And you can specify certain parameters too. So here I'm just going to select none because I will import the geometry from my local storage device. So I'm just going to click on import. I'm going to go into webinar and yeah, this is the cleaned geometry that is ready to go in SI units. So as you can see, the geometry has been loaded onto the website and it shows you how much storage that STL file is going to use. So you also have other options to transform your STL while at import time itself. You can scale the geometry if your units are not according to your needs. Presently, the units of our geometry are already in SI units, so I'm not going to make any transformations here. You can also rotate and translate the geometry at at your desired points. So I'm just going to import this geometry as it is. I'm going to click on import file. And depending on the size of your geometry, the time that it might take to load the geometry onto your GUI window might vary. For us, hopefully, it shouldn't take too much time. Yeah. So yeah, that was quick. So you can see you can see a transparent view of the geometry that we've imported. We have the cuboidal domain here, which are uh, the dimensions of which are essentially said to be in accordance with the wind tunnel dimensions of Ahmed's experiment in 1984. The reference can be found in the previous slides. You can go through the recording of the webinar for the same. The geometry inside is the Ahmed body. I've placed it at a distance of 50 millimeters from the ground, which is the designated ground clearance. You can't see it exactly here, but yeah, the geometry is floating at a height of 50 millimeters from the ground. So it essentially, as soon as you load the geometry, it essentially populates a list of patches that are part of the STL file here. So we have, if you go through the ABNS patch, which is the Ahmed body patch, you can set your specific resolution according to the grid strategy that you've employed. So Taral offers two different strategies. One is single resolution. One is a single resolution grid where you essentially set the same resolution for the entire entire domain that is to be simulated. And the distinguishing feature that we offer is a multi-resolution grid, which essentially enables the user to select specific regions of interest and refine them with higher accuracy, so as to get a solution, get a better solution at those specific regions of the domain. So this also reduces the amount of storage that the user has to make use of. Uh, so here I'm going to set a resolution of 0.0036 meters on the Ahmed body patch itself. This corresponds to around 80 points on the height of the Ahmed body. So I'm just going to select set resolution. I've typed in the resolution and I'm going to save this setting. So that particular setting has been saved, and the rest of the patches, the rest of the surfaces, I'm going to let them stay at the project resolution itself. So regions, essentially, we have to set information pertaining to regions. Regions essentially are distinct volumes in your STL geometry. So if you can see here, we have one volume that is inside the Ahmed body, one volume outside the Ahmed body, but inside the cuboidal domain that is essentially demarcated by the STL surface of the Ahmed body and the cuboidal domain itself. And uh, the third volume, the third region, which is not quite as obvious as the other two, is the the entire region that lies outside the cuboidal domain itself. And that region is added in the simulation workflow by default. It's known as the outside region. And I'm going to set the information for the same here. So the only information that SankhyaSutra Taral needs to be able to identify these regions accurately is a specific coordinate that lies anywhere in this particular region that you're setting the information for. So I'm going to let the region name stay as outside. I will select the geometry and I will set a coordinate 10, 4, and 0. So yeah, as you can see, you can view the point here. It lies outside the cuboidal region, and that essentially defines this particular volume. So there's two kinds of there's two kinds that you can select for a particular region. There's the simulate kind and the vacuum kind. we essentially don't solve the Boltzmann equation in the regions that are of vacuum kind, and we perform the simulation only in the regions of kind simulate. So I'm going to save this setting. Then I'm going to add the next region. I'm going to call it fluid, which is the name of the region which we want to simulate for. Select the geometry. I'm going to set the point accordingly. 520. As you can see, that particular point lies here. I'll just increase the point size by a little bit so that you can see. And I'm going to select the kind as simulate. I will save the settings. And the third region, which is the bulk region inside the Ahmed body, I'm going to name it as Ahmed underscore bulk. I will select the geometry and I will set the coordinate accordingly. So as you can see, the point lies inside the geometry, inside the Ahmed body geometry. I'm going to set the kind as vacuum and save. So that's the region part of it. And as I explained, uh, you can always set brushes which are cuboidal regions of interest that you want to refine with refine with a specific resolution, in order to uh, in order to get the solution at a desired level of accuracy. And as I explained, for the Ahmed body, the wake, which is the region behind the Ahmed body, is probably the most important region that has to be refined with a good level of accuracy in order to obtain accurate macro level features. So I'm just going to call this brush 1. I will set the bounds of the cuboidal domain accordingly, since I'm already familiar with the dimensions. For your geometry, it might be a little different. So the minimum starts at 0. And yeah, I'm going to I'm going to decrease the extent in the Z direction. So 0.2 and 0.2. So exactly the region behind the Ahmed body is going to be refined with the resolution of your desired choice. So I'm going to set the same resolution as the Ahmed patch itself, which corresponds to a height of 80 points, which corresponds to 80 points along the height of the Ahmed body. So I'm going to save this, and then we set we there's also a feature in Taral where you can check your grid without performing this entire simulation, and only if your grid is according to your needs and desires, you can then start your simulation and perform and solve for the variables of interest accordingly. So in this webinar, I'm not going to be covering this particular feature, as this will be covered in more detail in subsequent webinars, but it's something that's nice to have. And yeah. So if you look at simulation parameters, the first thing that would want to do is add your material properties. I'm just going to click on the plus beside materials. We have some default materials here in the library of materials, which are air and water. You can always add custom materials with specific properties of your interest, but for this particular case, I'm going to select air, and I'm going to go with air itself. And then you set your initial conditions, which are basically the uh, velocity, pressure, and temperature at the point of time whenever the simulation begins. So I will just call it IC underscore Amit, which is an arbitrary name. The region is obviously fluid because that's the region that we're going to simulate and solve for. I'm going to let the pressure stay at 1 atmosphere, or 101325 pascals. I'm going to set the velocity to be 41.89 meters per second, which corresponds to a Reynolds number of 768,000 for this particular simulation, which is based on the height of the Ahmed body. And then I'm going to set a temperature of 298 Kelvin, which corresponds to a temperature of 15 degrees Celsius. Then, so SankhyaSutra Taral has this nifty feature where it automatically populates a list of boundary conditions for you based on the list of patches that are present in your STL geometry. So you have to set boundary conditions for each of these patches individually. So for this particular problem, since we're trying to emulate the flow past the Ahmed body in a wind tunnel setup, we would be applying the no slip wall boundary condition on all of the side walls, which is essentially both the walls in the z direction and the y direction, and also the surface of the Ahmed body itself. We would be applying a constant velocity inlet boundary condition on the x minimum plane, and a static pressure outlet boundary condition on the x maximum plane. So if you go to BC underscore ABNS, the name is already typed in for you. There are different kinds of boundary conditions that we offer. We have the free slip, we have the static pressure outlet, constant velocity inlet, the symmetry BC, the wall BC, which corresponds to the no slip BC, no slip boundary condition, periodicity, and for moving geometry solutions such as rotating turbine blades or your impellers, etc. We also offer the moving wall boundary condition. The details of the moving wall BC and its features can be found in the previous webinar, and you can always go through all the previous webinars on the SankhyaSutra Labs website itself, and under the resources tab. So here I'm going to select wall, and yes, so basically we have to give some information to the solver for it to be able to identify which points it has to apply the boundary conditions on. So since we would want to apply the boundary condition on the fluid side, uh, our from region will be Ahmed underscore bulk, which is the volume inside the Ahmed body, and the to region will be the fluid region, which is where we want to apply the BC itself. And the surface has already been selected with you, so I'm not going to change that part. So select save, and I'm going to go to Xmax. Xmax is the outlet BC. The patch that we are editing, right, that we are setting the boundary condition for right now, is highlighted in red for ease of the user. So this is going to be from outside to fluid. Save. For Xmin, this is an inlet BC, so this is also going to be from outside to fluid. And the speed essentially is the velocity is 41.89 meters per second, which corresponds to a Reynolds number of 768,000, which is 0.7 million. So I'm going to save this. So Ymax, Ymin, Zmax, and Zmin, all four of them will have the no slip wall BC applied on them. So I'm going to select from region outside to region fluid. I'm going to save this, and I'm not going to set the boundary condition for the other three patches because we have a feature where you can copy the boundary condition from one patch to another. So since we've already set the boundary condition for BC underscore Ymax, I'm going to copy it to Ymin, Zmax, and Zmin. So I'm going to select those three, and I will click on copy. So it has been applied accordingly. So if you go to Ymin, it has already been set. So the from region is outside, to region is fluid, and we are applying the no slip wall boundary condition on the same. Right. So that's most of the simulation parameters that are needed to obtain the solution of your desired interest. So the last part is where you have to set your measurements, which is basically uh, where basically you selecting to save your simulation data, which is a solved simulation data, in certain formats at certain instances of time. So the first of these is a probe feature where you can select a specific point in your domain and choose the quantities that you want to monitor at that point with the passage of time within the simulation. So I'm just going to give a certain name to this. I'm going to call it probe underscore Ahmed. I would want to monitor the pressure data at this particular point because I would want to see the kind of fluctuations that the wake experiences for this particular simulation. So I will set a point of 0.53, a y coordinate of zero point 0.2, and z coordinate of 0. So this lies exactly behind the Ahmed body. Maybe I will take it a little away from the Ahmed body. So let me increase the point size. So yeah, that's where the point lies, and that's where I want to monitor the pressure data with time. So this gap time I will specify in terms of the simulation time itself. So if you want to run your simulation for 1 second and you specify a gap time of zero point 0.1 seconds, then you will essentially get 10 samples for whatever measurement that you specify the parameters for. So here I'm just going to select, I'm just going to give a really small time so that it prints at every time step so that we are able to monitor it at every time step. I'm going to save these settings, and then I'm going to add a volume measurement too, because I would like to monitor the velocity flow field at certain time instances, at certain planes in the simulation domain itself. I'm going to call this, sorry, I'm going to call this volume underscore Ahmed. I will specify a gap time of, again, 0.001 seconds. This, I would say, I would advise the users to be careful with this specific measurement, as it's quite heavy in terms of storage, but it also gives you a lot of information at hand. So only if you specifically need this particular measurement, I advise users to add this to your simulation workflow. So I'm just going to click on apply. Surface is essentially, as I said, you print the boundary points surrounding certain patches of interest to you. So I will just name this surface underscore Ahmed. I want to print I want to print this particular measurement because I would like to post process this data to obtain the pressure coefficient information on the top surface of the Ahmed body, which I will then compare with reference results. So I will save this data for the Ahmed body patch and also for the inlet patch, because I need the pressure and velocity details at the inlet in order to compute the pressure coefficient for my simulation. So I will just click on apply. And lastly, we have integrated quantities, which are essentially your forces in all three directions, all three Cartesian directions, which are x, y, and z. So I'm going to select this option because I would like to monitor the forces on my geometry as and when the simulation progresses. So I will select only the Ahmed body patch because that's the only surface that I'm interested on finding out the forces for. So I'm just going to select save. And finally, we will set the global parameters in terms of seconds, which is basically how much time you want the simulation to run for in the simulation space. So I will set a time of 0.72 seconds. This corresponds to a time of 100 convection times. It essentially means that the flow will the flow coming from the inlet will pass the Ahmed geometry 100 times. I will set a wall time of 1 hour since this is a demo simulation. You might want to save, you might want to change that according to your need. Yeah, oh yeah, before I said this, wall time is essentially the amount of real time that you want your simulation to run for. So this will determine how many, this will determine your core hour usage that has been allotted to you. So the number of cores, I'm going to let it stay at 128 cores. The project resolution, I will set it to 144. Uh, I'm sorry, 14.4 millimeters. This will give me three levels of refinement in my domain. So the finest resolution is 3.6 mm, which I had set previously on the Ahmed patch, and the coarsest resolution, which is also known as the project resolution, I'm going to set it as 14.4 mm. The reference length, I'm going to set it as 0.288 meters. This is essentially the height of the Ahmed body and also what our computed Reynolds number is based on. So set restart essentially is the same feature that I explained about before. It enables the user to save states of their simulation at certain instances of time. So there are two ways in which you can specify the frequency of saving these instances. You can specify them both in terms of steps or iterations of the simulation, or in terms of gap, that is in terms of seconds within the simulation space. So I'm going to set a restart time of 0.0072 seconds, which corresponds to one convection time. So yeah, that's all with respect to setting the parameters itself. And the last thing you do is the easiest step in this entire process, which is you launch your simulation. So I'm just going to click on launch. Hopefully we don't encounter any errors, and yeah, we haven't encountered any errors. So it basically performs a basic pre-submission check, which tells you whether there are any errors in your simulation setup. It tells us that there's no warnings or errors that were found, and the simulation run has been submitted. So there's a tab here that indicates the status of your job. Currently it is running. You can always monitor your simulation's progress in the solver log itself. So there's some information here printed for you, which gives you a better idea of what parameters have been exactly set for your simulation. So this is more related to the geometry, and this has more to do with meshing and uh, the amount of memory usage that your uh, current problem is currently making use of. So as you can see, the simulation has started. You can always refresh your log file by scrolling to the top and clicking on the refresh button. Uh, for more power users, we also have a user interface to offer where you can directly give the input script through Python and edit this according to your needs. So during the simulation, based on whatever measurements and integrated quantities you've set, you can monitor those quantities of interest in a live manner as and when the simulation progresses. So here I had set probe point. So this is density at that particular probe point with time. So the x-axis is time and the y-axis is density. So as you can see, it is plotting the density as and when the simulation runs. And the same goes for integrated quantities on the Ahmed surface itself. This plots the forces in SI units in newtons. You can non-dimensionalize this to get your drag and lift coefficient data. So I would like to move to the post-processing part of the demo. Since we've just started running the simulation, we won't have much data. So I've already run a simulation for you and kept the data at hand. So I will quickly move to that particular project. So I'm going to click on Open in Workspace. So this is a simulation where the run has already completed. If I go to the log, you can see that it has run for around 0.038 seconds in the simulation space itself. So I will quickly go to the post processing tab and show you how to create a sliced view of the volume data that has been printed. So I will expand the slice option. I will create a new slice essentially. Here I enter a name for your slice. I will just call it slice2 underscore Ahmed. I will give the origin of the plane that I want to slice. So here you can also visualize the plane where your slice is going to be obtained at. The origin, I'm going to keep it as 000. The normal is essentially the normal to the plane. I'm going to let it stay as 001. And this is the wall time for the job that is going to be submitted for obtaining the slices of the domain itself. So I'm just going to keep this as 1 hour because this again is a demo. Wouldn't want to use too many resources. I will specify the number of cores as 64. And you can also specify the indices of the start and end frames for which you want the slices to be obtained. So I will not run this. As soon as I run this, the job will be submitted and the slices will be obtained. But since I've already run another instance of this particular job, I will quickly jump to that and show you the results for the same. So as in when you obtain the slices, this is what your view will look like. I will click on the Z normal view, and this is essentially where you can select the index of the slice that you want to visualize. I will quickly jump to an intermediate slice so that you're able to view the flow features. There's different views that the post-processing tool of SankhyaSutra Taral supports. So this is built on the VTK library itself, and we have analogous options to suit your interests. So I'm just going to stay with surface, but you can always view other points where you'll get a better idea of what your grid looks like. You can also select the color scheme which you through which you want to visualize your data. So I'm going to select cool to warm because that's my favorite. And this is the this essentially gives you an option to select the data that you want to visualize. We'll just select velocity because that will give us a better idea of what the flow looks like. I'll just quickly hide the geometry so that you can have a better look at the flow field itself. So this is what the flow field looks like. I will just try to zoom in a little bit. So the flow comes from the inlet, hits the body, travels over the midsection, and partially separates and reattaches over the rear slant of the vehicle. So essentially, for the Ahmed body problem, there's three quantities that people look at. It's those three quantities are the drag coefficient, the lift coefficient, and the velocity profiles. The drag coefficient you can obtain by non-dimensionalizing the force data that you can visualize in the main screen itself. The lift coefficient again can be obtained through the same methodology. Whereas for the velocity profiles, you might want to take slices at certain instances for a specific window of time, for a specific number of cycles after your simulation has settled and reached a transient statistically steady state. And then you time average that data and run it through a few scripts so that you can plot both your time average data and the reference data in the same plot and do a one-to-one comparison. So I've already done that for you. I will quickly jump to the results part of it. That's it for the demo part of it. If you have any questions, please feel free to drop them in the chat window or to Ashwin. There's also other features that we offer in the post-processing tool that we will explore in subsequent webinars. So I'll just quickly jump to the results. So this is just a few things that I spoke about during the simulation itself. So these are the sample results. I've run simulations for 1, 2, 3, 4, 5 different resolutions. The closest resolution that I started with was 3.6 mm, which you can see is the data point here. The error in drag coefficient for that particular resolution is quite high, around 70%. But as you keep refining your simulation, the error goes down, and the final error is around 3.6%, which is within the accepted limits of automotive industry standards. So the same goes for the lift coefficient too. As you increase the resolution, the error goes down, and you get an error of around minus 2.5% as compared with the results of Bayraktar et al. The reference for the same has been added here at the bottom of the slide for your perusal. And with the surface data, you can also post-process the time averaged surface data that you might have printed in your simulation and then plot it against reference data in order to be able to validate your results. I also have so these are the velocity profile results that I had spoken about. This is basically the time averaged slice data. So from a dx min of 1.8 mm to 0.225 mm, you can see an improvement in the results. So that was it for the demo for today. So SankhyaSutra Taral basically enables you to perform quick simulations for your automotive solutions. So if you have any questions, please feel free to